and stereoisomerism. Under structural isomerism, it is further classified into four, which are chain isomerism, positional isomerism, functional group isomerism, and tautomerism. Hello students, good day and you are welcome back to my channel. If this is your first time of tuning in, please consider subscribing. Very quickly, we are going to be looking at a very important concept in organic chemistry termed isomerism. And now let us quickly see what isomerism is all about. Like I have on the board here, it is a phenomenon whereby an organic compounds have the same molecular formula but different structural formula. Very, very important. So a phenomenon whereby organic compounds have the same molecular formula but they now differ in their structure. That phenomenon is what is called isomerism in organic chemistry. And most importantly, again, I also want you to understand that there is a such thing like isomer. Isomers are those organic compounds that possesses this phenomenon. All right, that is, isomers are organic compounds having the same molecular formula but different structural formula. So the phenomenon is what is called isomerism, while those organic compounds that possesses such phenomenon are isomers. All right, very importantly, I also want you to understand that this isomerism is broadly classified into two, which are, I will call them the classification. So the classification of isomerism. The first classification, they are classified into two, like I said. The first one is structural. The first is structural isomerism, and the second is stereoisomerism. All right, so these are the two broad classifications of isomerism, the structural isomerism and the stereoisomerism. Now, don't forget, these are the two classifications. This first classification, which is the structural isomerism, is further classified into four, and the second classification is also further classified into two. All right, so for the first one, which is structural isomerism is classified into four, which are, so let me just write it down. So under structural isomerism, we have the first one to be chain isomerism. The second one is positional rather. Positional isomerism. The third one is functional group. Functional group isomerism. Then the fourth one is tautomerism. Okay, now very quickly, like I said, don't forget, isomerism is classified into two, structural isomerism and stereoisomerism. Under structural isomerism, it is further classified into four, which are chain isomerism, positional isomerism, functional group isomerism, and tautomerism. Now, let me quickly tell you, let's see the definition of structural isomerism. All right, so very quickly, let us see what I have here. Structural isomerism. This is a phenomenon whereby organic compounds have the same molecular formula but differ in their shape of but differ in the shape of their carbon chain, position of their substituent, type of functional group, and displacement of their pi electrons. Alright, so this is the definition of structural isomerism. But don't forget that I told you that structural isomerism is classified into four. So all these classifications of structural isomerism are all captured in this definition of structural isomerism. Now, very quickly, what is chain isomerism? Chain isomerism is a type of isomerism whereby organic compounds have the same molecular formula but now differ in their carbon chain. Alright, so very quickly, so you take down this note, then let us take this isomerism one after the other. So this is the definition of structural isomerism. Very, very important. So let me also say something very important here. So when we say that it is a phenomenon whereby organic compounds have the same molecular formula but differ in their shape of their carbon chain. Now, if it differ in the shape of their carbon chain, it means that this one now captures the definition of chain isomerism. Again, if it differ in the position of their substituent, that is position of their substituent, it means that this second part now captures the definition of this positional isomerism. Again, type of functional group, it means that it captures the definition of functional group isomerism. Then finally, the displacement of their pi electron, it means that it finally captures the definition of tautomerism. Very, very quickly. So let us see the first type of structural isomerism, which is nothing but chain isomerism. Okay, so under chain isomerism, like we said before, it is a phenomenon whereby two organic compounds have the same molecular formula but now differ in their carbon chain. So that is all about chain isomerism. So if I have C5H12, for instance, this compound is nothing but pentane. This organic compound is called pentane. This compound now, if I want to draw the structure, I can have this. I can have CH3CH, 2CH, 2CH, 2 and CH3. So 1, 2, 3, 4, 5. This compound is nothing but pentane. And of course, it has 5 carbon atoms and 12 hydrogen atoms. So I have 1, 2, 3, 4, 5 carbon atoms. So if I should count the number of hydrogen atoms here, I have 3 here, plus 2 here, 5, 6, 7, 8, 9, 10, 11, 12. So C5H12 is the molecular formula of this compound, and this is the structural formula. Of course, I can as well have another organic compound that have the same molecular formula but now differ in structure. So it can be CH3, CH3, CH2, and CH3. So if you watch carefully, this one again, it has 1, 2, 3, 4, 5. It has C5. What about hydrogens? This is 3, 5, 6, 7, 8, 9, 10, 11, 12. So if you watch carefully, this is C5H12. This is also C5H12. So they have the same molecular formula, but they have different structures. So because their structural formula now differ as a result of their carbon chain, that is why this is a good example of chain isomerism. Chain. Okay, so what about positional isomerism? Okay, let me also extend positional isomerism with an example. As for positional isomerism, it is a phenomenon whereby organic compounds have the same molecular formula, but now they differ in their position of their substituent. So the substituent attached will differ in position. For instance, if I have a compound like this, like CH3, CH2, CH2OH. This compound, okay, the molecular formula of this compound is nothing but C3H5, 6, 7, 8. C3H5, C3H8O. Alright, and I can as well have another organic compound of similar structure, which is CH3, CH2, no, CH, then OH here, okay, CH3. Okay, so if you watch carefully, these two compounds, they have the same molecular formula but different structure. Okay, let's check out. This is 1 carbon, 2, 3, so C3. What about hydrogen? I have 3 here, 4, 5, 6, 7, 8. All right, so this is C3. This one is still C3H8O, and this is also C3H8O. So because both of them, they have the same molecular formula as this, but their structure differ. Now, their structure differ as a result of the differences on where the attachment, or maybe where the substituents are attached. So the substituent in this first compound is OH, and the substituent in this second compound is also OH. So this OH is attached on carbon number 1. This is carbon number 1, this is carbon number 2, and this is carbon number 3. So here, this is carbon number 1, this is carbon number 2, and this is carbon number 3. So if you watch carefully, in the first compound, the substituent is attached on carbon number 1, while in the second compound, the substituent is attached on carbon number 2. So now the substituents differ, or that the attachment of the substituents differ, while the substituent, as in while the molecular formula still remains what it is. So it is an isomer. So these two compounds, they are isomer, but the kind of isomer here is positional isomerism due to the position of attachment. Okay, quickly, the next type of isomerism under structural isomerism still is functional group isomerism. Again, this functional group isomerism is a type of isomerism whereby two organic compounds or two or more organic compounds have the same molecular formula but now differ in the type of functional group they have. So the only thing here, what we need to understand in this third case is that their functional group, the type of functional group the two isomers we have will not be the same. This example is clearly found in the case of ethanol and diethyl ether. A good example is CH3, CH2, OH, and CH3O, CH3. So these two compounds, they have the same, they have the same molecular formula but different structure. So this is a structure of ethanol. This is a structure of dimethyl ether rather. So this is ethanol, and this is dimethyl rather. Okay, this is ethanol and this is dimethyl ether, and the molecular formula is nothing but C2H5OH. Or, okay, let me put it more clearly. It can as well be written as C2H6O, most preferably. So if I buttress on this one, this ethanol, you can see that I have 2 carbon atoms, hence C2. And as for the hydrogen atom, this is 3 hydrogen, this is 2. So 2 plus 3 should be 5, plus 1, which is 6. Now this O is this O here. What about this? This is 3 hydrogen, hence H6. And these are the 2 carbon atoms, hence C2. And finally, this oxygen here, O. So these 2 organic compounds, they have different functional groups. So you can see, since they have the same molecular formula but different structure, they are isomers. But what kind of isomer are these 2 compounds? They are functional group isomer because they do not possess the same functional group. Ethanol possesses a functional group of OH, while dimethyl ether possesses a functional group of O. Alright, so this is under this classification of functional group isomerism. Now, what about tautomerism? I think I need to clean off this part and explain that concept very well. Okay, now in understanding tautomerism is nothing but a phenomenon whereby 2 or more organic compounds will possess the same molecular formula but now differ in their keto and enol form. Alright, now for us to understand their differences, we must understand what is keto form and we must as well understand what is enol form. So this is what I mean by keto form, and this is enol form. So the movement, or maybe the transformation of an organic compound from keto form to enol form, or from enol form back to keto form, that process or that phenomenon is tautomerism. So tautomerism is actually the movement or the transformation of an organic compound from a keto form to enol form, or from an enol form back to a keto form. So the transformation is what is called tautomerism. Now, and these two compounds that are tautomerizing from keto to enol form or from enol form to keto form, the phenomenon is called tautomerism. And the two compounds are isomers because they, even though they will have different structures as a result of that tautomerism, but they will still have the same molecular formula. But for us to understand this concept very well, this tautomerism always, or maybe actually, arises when alkyne reacts with water in the presence of conc H2SO4 to give us enol. First, we need to understand, let us take this alkyne. If we have CH3, CH3C triple bond CH like this, and these organic compounds reacts with water and in the presence of H2XO4. So if these organic compounds reacts with water in the presence of, so this addition means plus water in the presence of this as a catalyst, what it will form, this will follow Markov-Nichols rule, and this is going to form an enol. This OH, this water will break into two components. Water will break into two components, which are H and OH. So the H and OH, both of them will add into these two carbon atoms that are unsaturated. So this CH3, I will write it as it is, like this. Then over here, I will now have this C, OH here. Now C, this is the H. Now, and this is also another H, and there will be a double bond here. In fact, the whole idea about this mechanism is that these two carbon atoms are the two carbon atoms that will gain these two species of water. Don't forget that this H2SO4 is a catalyst. It is not the only part it is playing in this chemical reaction is that it is just there to accelerate the rate of the reaction. All right. While this water will split into its two species, such that one of them will add here and the other one will add here. Like I said before, this reaction will follow Markov-Nichols rule, which states that in this kind of addition reaction, that H will enter into the carbon that with more number of hydrogen, while OH will enter into the carbon with less number of hydrogen. So if you watch between these two carbon atoms in question, this has more hydrogen than this. Of course, precisely, this one has one hydrogen, while this one has no hydrogen at all directly attached to it. That is the reason why this OH will now enter into this one that has less number of hydrogen. Hence, I have OH here. And this H will enter into this one that already has a hydrogen. Hence, I also have this H here. But if you watch initially, there is a triple bond here, and by result of the attachment, one of the pi bonds present in this triple bond will be broken such that these two species will be attached. Then finally, I now have double bond left. So this is what I have. So it therefore means that whenever alkyne, precisely this is propyne, reacts with water in the presence of H2SO4, I will have this compound. And this compound is generally known as enol. Alright, so now, but I want you to understand that this enol is an intermediate, or this enol is unstable. So because of the instability of enol, it will transform itself from enol form to keto form. And by that, I mean, so I will have a reversible arrow, because even the keto form that is going to be formed here can sometimes be transformed to enol back, because the enol is unstable. But the most stable one is the keto that will be formed. So for keto to be formed from enol, what will happen is that this OH here, this hydrogen attached, or maybe this hydrogen on this OH will leave here and come here, while this double bond will leave here and come here. So generally, I will have this CH3 here, and I'll have C here, I'll have single bond here, I will now have C here, I'll have H, and H. So this is, now remember I told that this double bond will leave here and come here, so I will now have the double bond here. Now O is here. The hydrogen that was here initially has now left here to come on this carbon atom. Meanwhile, these are the two hydrogens initially attached. So that hydrogen that lives here and come here will now attach itself here. So this is nothing but the keto form. So this is the enol form, and this is the keto form. Okay, don't forget that I'm not really talking about mechanism of a chemical reaction. I'm trying to talk about isomerism, which precisely tautomerism. And I say that tautomerism is a phenomenon whereby organic compound transforms itself from enol form to keto form. So I chose a precise example So this is the inner form of this compound, and this is the keto form of this compound. If you watch carefully, let us count the number of carbon, hydrogen, and oxygen atoms on these two organic compounds. So for this, I have 1, 2, 3. I have 3 carbons, so I have C3. What about hydrogens? This is 3 hydrogens. 4, 5, 6. I have H6, then O. Then what about this? I have C1, 2, 3. I have C3. What about H? This is 3, 4, 5, 6. This H6, then 1O. So if you watch carefully, these two organic compounds, they have the same molecular formula, but now different structural formula. Alright, so because they have the same molecular formula but different structural formula, that was the reason why they are isomers. And the kind of isomerism that gave rise to this kind of isomer is tautomerism. So that is why tautomerism, even though it is one of the processes in chemical reaction in organic chemistry, it is also considered as one of the kinds of isomerism. Alright, so this is it about structural isomerism. Don't forget we are talking about isomerism, which is broadly divided into structural and stereoisomerism. Under structural isomerism, we saw chain isomerism, functional group isomerism, chain isomerism, positional isomerism, functional group isomerism, and tautomerism. Now, the next one we are going to see now is stereoisomerism. Okay, as for stereoisomerism, this is a phenomenon whereby organic compounds have the same molecular formula but differ in the arrangement of atoms in space. This is very, very important to understand. So, whenever two or more organic compounds have the same molecular formula but differ in the arrangement of their atom or atoms in space, that kind of isomerism is classified as stereoisomerism. Very, very important. And I want you to also understand that this stereoisomerism is also of two types, which are geometrical isomerism and optical isomerism. All right, so this is it. And geometrical isomerism now says that this is a phenomenon whereby organic compounds have the same molecular formula but differ in the arrangement of their atoms caused by non-rotation of groups about carbon-to-carbon double bond. All right. Then what about optical isomerism? This is a phenomenon whereby organic compounds have the same molecular formula but differ in their polarized light. Okay, so these two types of isomerism will help us to understand this stereo. All right, but just understand that this stereo is a compendium of these two. All right, these two put together makes up this stereo isomerism. Very, very important. Okay, let me just quickly clean off this, but just so that this is the definition of stereo, let me clean off this and carefully explain these two types of isomerism, probably with some examples. All right. Okay, now as for as for geometrical isomerism, this is a situation whereby two or more organic compounds have the same molecular formula, but now they differ. Now, how do they differ? They actually differ based on their rotation in space, locked by the carbon-to-carbon double bond. And I want you to understand that there are two kinds of isomers as far as geometrical isomerism is concerned. That are the types are we have Cis Isomers and we have trans isomers. All right, so these are the two kinds of isomers we can encounter in this geometrical isomerism. So now I will give some examples and I will now explain further what I mean by cis isomers. All right, so if I have carbon to carbon double bond like this, and on this carbon I have CH3, and here I have CH3 facing downwards here I have H, and over here I have H. Again, I have a similar thing like this, carbon to carbon double bond. I have H here, I also have H here, and I have CH3 facing downwards. I also have CH3 facing downwards. These two organic compounds, they are same in terms of having the same molecular formula, but they are different in terms of their structural formula. If you watch carefully, consider this carbon to carbon double bond as the central species here. All right, if you now watch on this carbon atom, the CH3 is attached on top, and on this carbon, the CH3 is attached downwards. Again, on this very compound, the CH3 is attached downwards, and on this one, the CH3 is also attached downwards. So what I want you to understand is that on this carbon atom, the groups are attached on opposite sides, and on this one, the groups are attached on the same sides. So notice that I'm trying to explain this too. So whenever the groups are attached on opposite sides, that kind of isomer is geometrical isomer, precisely trans isomer. And whenever the two groups are attached on the same side, it is still under geometrical isomer, precisely cis isomer. So opposite sides trans and the same side cis. All right. So these are the two kinds of isomer you will encounter under this geometrical isomerism. So that was why we said that they are organic compounds with the same molecular formula. Okay, let us try and see whether they have the same molecular formula, because for it is obvious that they have different structural formula due to the arrangement of the atoms in space. Okay, the molecular formula of this is actually 1, 2, 3, 4. So C4. What about H? You have 3 here, 4, 5, 6, 7, 8. So C4, H8, and I believe the same thing applies here. Okay, so this is C4H8, this is also C4H8. So the molecular formulas of this and this are the same, but their structural formulas are different because the species that are attached in space are this and this. And as for this compound, the species that are attached in space are this and this. So over here, the species are on opposite side, and here the species are on the same side. So because of that, they are considered to be isomers. So these two compounds are isomeric to each other. This one is trans isomer, this is cis isomer. Another important example is this. If I have carbon to carbon double bond, and here I have Cl attached, here again I have Cl attached, here I have H, here I have H. Now, you now watch, okay, I can have another one like this. Here I have carbon to carbon double bond. Here I have Cl, here I have Cl, here I have H, here I have H. So if you now watch carefully, these two compounds, they are the same in terms of molecular formula, but they are different in terms of their structural formula. Precisely, they are isomer to each other, because on this very compound, these are the two identical groups, and on this very compound, these are the two identical groups. So here, the two identical groups are on the same side, hence it is cis. And here, the two identical groups are on different or opposite sides, hence it is trans. Very, very important. So it therefore means that if you want to name this compound, you must use the word trans before naming. Very, very important. Okay, let me quickly clean off this and show you more clearly what I mean. Oh, this is optical. Okay, so if I want to name this compound, for instance, this particular one now, I will, of course, follow the basic rules of nomenclature, and I will have to say it is trans. I will start the name with trans. Now it will be trans but2-ene. While if I want to name this, it's going to be cis but2-ene. Okay, so they are, the only thing that differentiates both of them is that this is trans but2-ene, this is cis but2-ene. So if I also want to name this one, I will first of all start with cis. It's going to be cis 1,2 dichloroethene. All right, I'll have to end it with ene because it has it is the compound is alkene. Okay, very quickly, if I want to name this, it's just the same naming, but I will now have trans here. Trans 1,2 dichloroethene. Okay, so this is it, all right? But I'm not actually talking about nomenclature in organic compound, but I'm trying to make you understand what I mean by geometrical isomerism. That in geometrical isomerism, the isomers there are of two types. You have trans isomer when the groups are of opposite sides, and you have cis isomer when the groups are on the same side. All right. Okay. Very quickly, let us talk about the last one, which is optical isomerism. Very quickly, optical isomerism. Okay, as for optical isomerism, there is something very important I want you to understand. Like I have here, let me quickly read what I have here. It says, this is a phenomenon whereby organic compounds have the same molecular formula but differ in their polarized light. Of course, in any kind of isomerism, it must be a situation whereby two or more organic compounds will have the same molecular formula. But what will now make it what it is what will follow after it has possessed the same molecular formula. So it possesses the same molecular formula for optical now, but it now differ in their polarized light. So it means that if light is incident in this organic compound, their structure can change. So because their structure now differ, by reason of light being incident on them, that is why we call the isomers under that concept optical isomerism, because the concept optics means light. All right, and I also want you to understand that the compounds that will possess this optical isomerism, those compounds must contain a chiral carbon. So if a particular compound does not contain a chiral carbon, it means that it may not possess optical isomerism. Now the question is, what is a chiral carbon? Chiral carbon. Okay, so a chiral carbon is a carbon that is surrounded with four different groups. For instance, if you have a carbon atom like this, and of course this is a carbon atom, it must have four attachments, and you have A, B, C, and D attached to it. So I'm trying to use arbitrary. Okay, let me use E here. Okay, if I have a carbon, this is carbon, then it is attached to four different species, A, B, D, and E. So these are four different species. So because this carbon atom is attached to four different species, this carbon will be called a chiral carbon. Like I said, a chiral carbon is a carbon that is attached with four different species. Okay, using a precise example, I can have a carbon atom attached to CH3, the same carbon atom attached to OH, the same carbon atom attached to H, and the same carbon atom attached to Cl. So you can now see that this carbon atom is attached to hydroxy group, hydrogen, methyl group, and finally chloride group. So because this carbon atom is attached to four different species, not four identical species, or not species whereby two or more is identical, it's four different species entirely. Such carbon is termed a chiral carbon. And we are saying that any compound having a chiral carbon will have the ability to possess optical isomerism. And we also see that isomerism occur when light is incident on it. Whenever it rotates a polarized light, an isomer will be formed, and such isomers are called optical isomers. And now, very importantly, I also want you to understand that if light is incident on any chiral carbon, that chiral carbon could either rotate right or it could either rotate left. Okay, let me show this. This is carbon and this is hydrogen here. And here I have OH attached, here I have Cl, and I have CH3. So light can be incident on this carbon atom. Light can be incident on this carbon atom, and if light is incident on this carbon atom, it could either rotate right or it could either rotate left. If it rotates right, it will be called dextro rotation, and if it is rotated left, it will be called lateral rotation. But primarily speaking, I want you to understand how we can have two isomers here. So if this is considered to be a mirror, for instance, look at how this thing works. This is a mirror. This part is the polished surface. So this molecule is in front of a mirror. And the image, if this molecule is in front of a mirror like this, the image of this molecule will be shown on this part. It will be shown on this part such that this carbon will be facing like this. And this hydrogen is still facing as it is. Then this CH3 now, which is on this part, will now come on this part to be 3H. Okay, let me quickly clean it and draw it more clear. I'm going to have C, this H is still here. Now over here, I'm going to have H3C, I'm going to have HO, I'm going to have Cl. Okay, so these two compounds, they will possess the same molecular formula. Of course, these two things, let us write out their molecular formula. It's going to have C5. Okay, so this is 3, 4, 5. Okay, 2 carbon, one oxygen and one chlorine. So this is C2H5OCl. C2H5OCl. So the same thing applies here. So this molecular formula is for this and also for this, but they have different structural formula as a result of them rotating polarized light. And I want you to understand that if it rotates polarized light to the right, it will be called dextro rotation. But if it rotates polarized light to the left, it will be called lateral rotation. So that is majorly the whole idea about this optical isomerism. Thank you. So please like, share, and comment in this video. Thank you.